Greetings, the Astro 30 here again, and welcome to part 2 of this classic D Class D amplifier build. Well, here's our power supply board. You can cut this section off. This is for the 15 volt rail there to power a preamp. I couldn't even think where I was going with that. It should be relatively simple to assemble. Yeah, it's not that overly difficult. They don't supply the parts like the regulators, but I've got regulators. Don't know about the capacitors though, but we'll have a look. This schematic is basically a repeat of the one that's in the actual amplifier schematic, so you can use either, but that's basically all it is. It's just a 35 amp 600 volt bridge rectifier, which I can't see in the board in the bag of parts at the moment. It should be there, they should have supplied it, and 6 4700 microfarad capacitors at 63 volts each, and 2 LEDs. One is to discharge the capacitors and the other show that the power is connected, so I can choose either one of those to mount to the front panel as a power indicator. But for all intents and purposes, it does, these LEDs don't really need to be in there. You'll just have a fair amount of charge on the capacitors there. But I'm trying to look for this bridge rectifier, which is completely missing. So there's no bridge I see. They've got the rectifier separate from the board, which is kind of annoying. So you'd actually use one of those panel mount ones to bring it down to earth, or to the case, to help heatsink it. So yeah, that could be a little bit of a problem because I don't have such a bridge rectifier, and they didn't actually tell me to buy one. Great. So anyway, practically speaking, I don't think I can go any further with this amplifier module today. However, I will assemble this board, and this is only single-sided, so yep, I'll assemble this board and then we'll come back. Okay, that's the power supply assembled for the most part, apart from the 3K 5 watt resistors and the 2 LEDs, but because I don't need them right at the moment, you are supposed to put them on there to act as bleeding for these capacitor banks here. But for this low side, you're going to need either a separate 15 volt transformer, or a transformer with multiple taps, with the high side and the low side taps on it, which can be next to impossible. Bridge rectifier comes in from on these pins here, and that's basically it for that. It's not all that exciting. You're going to have to purchase your own connectors. I see. Here's the full schematic of the power supply. Got your 35 amp bridge rectifier over here supplying the plus minus 57 volt rails respectively, with 2 connectors for each power amp module. Over here we got a D1 to D4 forming a full wave bridge rectifier using 1M4004s, 2 15 volt regulators. This is actually an output for 30 volt AC, so that's not doesn't mean you need to have an extra tap there, because the transformer's over here. That comes from the 2 combined 15 volt windings over here. So you'd need a 300 VA at least, 2 times 2 40 volt, so that it'd be a 40040, 300 VA for the high side, and plus 2 times 15 volt at 7.5 VA, So you need a toroidal transformer, which is double winding, so you've got 2 highs and 2 lows. They do make them, but it doesn't actually say so far what model of transformer to use. So that's the schematic of wiring up everything. This is also used for the ultra low distortion power amp module that they're describing. So yeah, you have your 15-0, 15-0, 40-0, 40-0 going in different places here. And yeah, in order to find that transformer, you probably, for a multi-tap winding like that, you're probably going to be paying big bucks, because the main transformer is going to be 300 VA. So for my testing purposes, which I'm not going to do today in this video, I'm not going to shoot it today, I will shoot it on Sunday, so this video is going to be delayed in being uploaded. We'll use those two 30-volt transformers just to get things working, and then when I decide to put this in a case or whatnot, we'll worry about, you know, correct transformers and shit if I want a 15-volt, 15-volt rail for powering a preamp or not at a later stage, because let's face it, all we're interested in is seeing if this module actually will now work that I've assembled it. It should do. I haven't tested it yet, obviously, but that'll be the next step. But yeah, but for now I'm going to leave that testing till Sunday, which will be the next part of this video. Just one last thing before we move on to testing. I had a quick look online, and you cannot get the kit for the loudspeaker protector for this project anymore. Not on JCar, not anywhere on eBay, and not anywhere in Alltronics. And Alltronics are also running very low on the actual amplifier modules, so if I want another one to build stereo, I'm going to have to buy one pretty soon. But you can still buy the PCB directly from Silicon Chip magazine publications. Just go on their website and just look for it. So yeah, that's the only problem, is that that's not available as a kit anymore, which is annoying. But yeah, you can still get their PCB, so that'll be probably worth investing in later when I can be bothered. But now we'll just move on to testing of the actual main amplifier, see if it's you know, worth the money. I hope it bloody is, and I hope it works after all this effort. We'll soon find out. Okay, it's time for testing the amplifier module, but first I'm going to need to build a suitable AC supply. I'm using these two transformers, which I've just found out they're actually 15-0, 15-0. So there's actually two separate secondary windings, both with a 12 volt and a 15 volt tap plus a 0. So in order for this to work, which is going to be awfully fun, is I'd have to wire one 0 to the other 15. So we'd have a 15 and a 0, and then they'd have to be wired in phase with the next one in the same configuration to give me the 60 volt AC that I need. And it's pretty easy to do that if you wire it the same way. So if you go from the 0 lug to the 15 and take it off of the 0 here and the 15 there, the next one would be the 0 goes to the 15 over here. Those two form the center tap, and then, well, the 0 and the 15 over here get joined, and the 0 then forms the the neutral, and the 15 over here forms the active. Now, I know that sounds a bit complicated, but it'll make sense when I actually show you on a whiteboard. As for the bridge rectifier, I'm going to use one of these GBJ810s. This is what I mean with the transformers. Basically, this is TR1, TR2. The first transformer will take one of the 15 volt taps off. That becomes our active. The 0 of one winding is attached to the 15 of the second. The 0 of the second goes off to the 15, the first 15 of the second transformer. Again, the 0 and the 15, the 0 from the first secondary is attached to the 15 of the second secondary, and then finally this 0 forms the neutral, and this bit in between the two transformers forms our center tap. So that's basically what I meant, and that's how I'm going to wire the transformers. Okay, I got both transformers wired up as they should be. I've got the multimeter hooked up across the resultant plus and minus, or active and neutral, of both transformers, so that's combined. This red positive wire here, which is the active, and this green, which is joined to the other transformer as well, that's the center tap, should be 30 volt across that. And conversely, this black wire, which is the end of the other transformer, and this center tap should be 30 as well. And across both should be 60. If there is only half the voltage across there, like there's only 30 volt across the whole entire thing, that means the transformer is wired out of phase, or 180 degrees out of phase. Anyway, this is before I've hooked it up to a bridge rectifier. This is just testing that the AC side works. So I'm going to plug it in. Hopefully nothing goes off bang. And we have 64.6 volt AC. So that's well with where I wanted it to be. Okay, so now I've got the bridge rectifier hooked up as if it was in AC. Well, it is AC. But I've carefully bent the two negative and positive leads out a bit so that these jumper wires do not come into contact with each other. Unsmooth DC. We should see probably around about 70 volt on the meter, so we'll have a look. Oh well, my estimate was wrong. I was about 20 volt out, or 10 volt out. It's 57. That's unsmooth though, so if we now hook that up to the power supply, we expect to see around probably 86 volt. Alright, got the power supply module now hooked up to the transformer bridge rectifier Frankenpenis. I've got the multimeter on DC hooked up to the plus minus 57 volt rail on the output. Now nothing disastrous should happen, it shouldn't go bang or anything, but if it does, and it fails spectacularly, it'll be captured on video. Just as long as everything is wired the correct way round, and as long as the transformers are wired in phase, we should have around 70 volt at the output, thereabouts. Actually no, we should have closer to 42, 84. So I'll plug it in, and we have 87.9, 88 volt there. So that's about 44 plus minus. So we've got a good healthy 44 plus minus voltage rail there. Nothing went off with a bang. Now remember, the bleed resistors are not installed on the PSU board, so as soon as I unplug this, it's going to take a spectacularly long time to discharge. Okay, so now it's time to test the power amplifier module. Now we don't need the power supply connected for at least the first 4 steps. Okay, so when testing the actual amplifier module, there's 10 steps you've really got to follow in the instructions, and most of it's just measuring voltages. So step 1 is to install the jumper shunt across LK3, the protect header, just to the right of the trim pot, VR1. This places the amplifier in the protect mode so that it will not start up when power is applied. So the first step is to install a header across LK3, which is this one here. So that basically brings the protect circuit to ground. Step 2, install a jumper link on LK1 and a jumper on LK2 near the RCA sockets in the normal position, and a jumper on LK4 to allow the protect LED to light. LK1 needs to be connected so the ground lift is not lifted, and this needs to be connected in the normal position, that's LK2. You're supposed to jumper this connector LK4 as well to allow the protect LED to light, but unfortunately they don't actually have another jumper for that, so I'm just going to cheat. I'm going to short the connector, as long as the other end of that cable doesn't come into any contact with anything. Step 3, monitor the resistance between TP1 and ground and adjust VR1 to give a reading of 850 ohm. This sets the quiescent operating frequency for the amplifier to about 500 Hz. Now we'll notice straight away that we haven't powered the unit up yet, so really it makes no difference whether the fuses are inserted or not. Okay, with the multimeter connected in ohms mode across test point 1 and ground, we need to adjust the resistance on this variable potentiometer around about 850 ohms. So currently we're slightly high at 948 ohm. So if I turn this in counterclockwise position, we can see the ohmage is coming down. So we want 850 thereabouts. So I keep turning it until we're at 850. I will put a scope on the VS connector and or test point and see if it's at roughly 500 Hertz. So that should give us a quiescent frequency of 500 kilohertz. Step 4. Insert fuses F1 and F2, then connect a power supply to the classic D module, making sure the polarity is correct. Okay, at this point you can install the fuses. Well, they're already installed. And now we can connect the power supply to the module, making sure the polarity is correct. Step 5, switch on the power supply and check that the Protect LED, LED2 lights. Note that high voltages are present on the power supply and amplifier PCBs during operation. Do not handle or touch the power supply or the amplifier module with power applied. Otherwise you could get a severe shock. We apply power and hopefully nothing goes bang. So we should see this LED here light up, which we do. Step 6, check that the plus minus 50 volt or thereabouts supply rails are correct at COM2. Note these rails will depend on the power supply used. If these are correct, check that the VAA near Xenodiode 3 is at 5.6 volt, i.e. measure between VAA and ground. Similarly, check that both VSS near ZD4 and CSD are around about minus 5.6 volt. So now we need to check the plus minus voltage rails. Should be close to 44 in this case. Got 43 there and 43 there. They're where it should be. Nothing's getting hot. So now I need to check between VAA and ground, if I could get on there properly. We have 5.5, that's plus 5.5. And between VSS and ground we should have minus 5.5. We have minus 5.6. 5.6 is what I said. So we've got minus 5.6 there on VSS and VAA. Plus 5.5, so close enough. Step 7, check that VCC is around plus 14 to 15 volt, measure between VCC and COM. Then check the voltage across the output terminals at COM3, i.e. the speaker terminals. This should be around 1.57 volt with a 50 volt supply, but will drop to only 6 millivolt or less with an 8 ohm or 4 ohm load connected. So right away at the output we can expect to see a offset voltage of 1.57 volt unloaded, so keep that in mind. So between VCC and COM I should have around plus 14 to 15 volt. Yeah, I got 14.2 there, or I did. Yeah, 14.2, that's good. Now I need to check the voltage across the speaker terminals. It should be about 1.5 volt, which it is. So that's all good so far. Step 8, check the voltage between VB and VS. This should be above 9 volt but will rise to 14 volt or 15 volt when the amplifier is actually running, i.e. when it's no longer in protect mode. So far we're doing all these checks with the amplifier forced into protect mode. If any of the voltages in the above steps are incorrect, switch off immediately and check that all parts are correctly placed and oriented. You should also carefully check for shorts between IC1's pins, example solder bridges, and for shorts due to solder bridges on the underside of the PCB. Now the voltage across VB and VS should be close to 9 volt, which it is. I've probably got it backwards, but it's negative 9 volt. Yes, that's correct. So now that that's passed those voltage measurement tests, I can switch it off. Step 9, if the voltages are correct, switch off, remove protect jumper LK3 and reapply power. After a second or two, the protect LED should turn off and the run LED, the blue one, should turn on instead. I can remove the protect jumper LK3 and I assume LK4 as well. So LK3 is removed. Okay, so if I now plug in the power, after 2 seconds that blue LED should light up. And it does. So we now know that the amplifier is functioning, so we can move on. So for now, I'm going to unplug him. And off goes the LED. Step 10, if you have a scope, so this step is not actually important, but if you have a scope or a frequency counter, the quiescent operating frequency can be measured at the VS test point near Q1. If you're building a stereo or bridged amplifier, the module should be set to run at the same frequency under no signal conditions to minimize distortion. That is, with no signal input applied. This can be adjusted using the trim pipe VR1. So you can do it in step 3 using the multimeter to adjust the resistance, or you could actually use a scope to get the frequency more closer to 500 odd kilohertz that's required. Okay, so I've got the DDS hooked up to the input, I've got the DSO at the output across an 8 ohm dummy load. I'm going to try and see if I've got an output. I've got times 10. Yes, I do have an output. I wasn't getting an output on the other scope before and I can't figure out why. At times 10 I can see at 1 volt in I'm getting 16 volt out. Okay, doesn't seem all that impressive, does it? But however, I don't know what the input sensitivity is. But it is a decent stable waveform, so let's up the amplitude to 2 volt peak to peak. And I don't see any clipping, so we go to 3 volt peak to peak. Have a look. We're still not clipping and we're pushing out 40 volt now. So we change the amplitude to 4 volt. And we're now outputting 54 volt. Heatsink is still cold. So I'll change the amplitude to 5 volt. It's 70 volt and it's not clipping. And it's starting to run out of current there, it's starting to clip. Well, the power supply was dropping in and out. So I'm going to ballpark it at 5.6 volt peak to peak input. We are slightly clipping, so I'll back that off to about there. I reckon 72 volt roughly. I'll say 72.2. Peak to peak is the maximum. So I'm not going to have that producing full power all day, so I'll drop that back down to 1 volt. So we're looking at 72.2 volt peak to peak. So we'll divide that by 2, gives us 36.1. Square that, which equals that, which is the highest figure I've seen so far, divided by the 8 ohm load. 162 watts. That is significant. That is very impressive. And yeah, once it starts going into clipping, it can start dropping in and out, oscillating on the output. But still, 160 watts clean power out of this little module is quite impressive for the plus minus 42 volt rail that we've got there. Now, I was trying to see what we had frequency wise between VS and COM before on the other oscilloscope, but it doesn't appear to be working, and I'm not exactly 100% sure as to why. I wasn't getting any output signal either. Whether it's a driver issue or the scope's fucked, I don't know. I might, before the end of this video, rehook back up that scope and just, see if it's miraculously working again, but I don't think so. Now, according to that crappy frequency meter, I am roughly at 459 kilohertz, or thereabouts. So, let's see what happens when I rotate the pot. The frequency is increasing. So practically speaking, if you have two of these modules, you would adjust it so that both frequencies were the same. So I know that the frequency is changing. So that's all well and good. I guess the burning question now is, what does it sound like into an actual speaker? Well, I'm sacrificing one of the desktop speakers here. I've got the DDS disconnected from the input. I've got the speaker hooked to the output. I'm going to plug it in. Slight little pop from the output. Well, we can hear output. I can't hear anything unusual coming out of the speaker, no hum or anything, so it is functioning. So I guess what we need to do is we need to hook it up to an audio source. Okay, I've got the CD player hooked up across a 50k linear pot. Should be a logarithmic, but don't have one. Log it in. Increase the volume slightly, and I'll play a track. Not sure what, but I'll play something. It does have a very high input sensitivity. Beautiful. So it is outputting an audio signal. It sounds relatively clean. I'm quite pleased. Heatsink isn't getting hot. Can't even feel it. And there's just one thing to note, that if you have two of these as a stereo unit, there is one phenomenon known as supply bus pumping, and basically what happens with Class D amplifiers is the power supply can be raised above its normal voltage by a process called supply bus pumping, and it's caused by the energy stored in the inductance of the output filter back here and the speaker windings of the coil, and then thus being fed back into the supply rail via the output MOSFETs. And this is primarily an issue for signal frequencies below 100 Hz, i.e. the ripple frequency of the main supply capacitors. So in order to prevent that, that's the other reason why we've got this jumper here to go from normal to inverting. One amplifier will be set to normal, non-inverting. The other amplifier would be set to inverting. And because now the second amplifier is 180 degrees out of phase, we just swap the output leads around on the output to the speaker, so that then that amplifier is now in the correct phase. And that will eliminate the supply bus pumping. So that's one problem or issue that is common with Class D amplifiers, and the way to solve it is to have one 180 degrees out of phase with the other. That's basically all to talk about that. I did go and buy a second kit, so I've got two of them now. This was the last one on the rack at JCar. I thought I'd better get it now before it's no longer there next week. Probably will still be. But I don't know about some of you in Tasmania that actually watch my videos that would actually go down to JCar just to buy the last kit just to piss me off. So I thought, well, okay, I'd go and buy the last kit. And the thing is, I got $9 off. They called it price match on the receipt, but he said trade price. So basically, this was $89.95. I got it for $80.95. So I got it for $9 off. Sweet. You could have probably got it cheaper online, yes, but seriously, what's the point? So anyway, I got the second one, which I'm not going to build today because it is very involved and time consuming, but that'll be for a later date. And we'll have a pair of them. The other thing was that you're going to need a very decent preamplifier with plenty of gain coming out, because this, as we found out, has a rough input peak to peak input sensitivity is around about 5.2 volt. So you'd need a preamplifier that could at least deliver 10 volt peak to peak output at full volume, just so there's a little bit of headroom there, so that the volume control's not all the way up to hear anything, which it currently is. But that's understandable when we're only going on a 1.2 volt maximum peak to peak output of a CD player. So you'd have a decent preamp. Even a preamp with a gain of 15 would probably be better, because they'll allow volume right down low, and you know, you've got plenty of wick there to play with. So that's the only thing I noticed, that yeah, it requires a hefty input signal in order to output the 160 watts. But that's impressive, 160 watts out of a 42 plus minus power supply rail, when the actual thing is designed for plus minus 52. I'm actually 10 volt less, maybe 8 volt. And the thing is, if you wanted to actually force this into protect mode, if you like you plug in a headphone adapter into a headphone socket and you want the speakers to mute, you could just simply bring the protect to ground, and well, the LED is not going to light up, but that'll actually mute the output. So if I play another track, and basically short this connector, signal drops out. Now, it won't hurt the amplifier, or at least it shouldn't. So just pause that a sec. Because if we look at our schematic of the protector circuit, and I did forget to mention in the last video that the output is also being monitored by these 3 transistors here, well, these 2 anyway, that's for the thermal, and these are detecting whether there's DC on the output higher than the 1.5 volt base voltage. So if one of those MOSFETs happens to short circuit and bring one of the supply rails straight to the output, well, it'll also trip the circuit into protect. However, LK3 is over here, which is basically bringing the emitter across to the collector. So all we're effectively doing by having that bridged is we are shorting the emitter to the collector. Now this won't hurt the transistor in any way, because we're not actually shorting the emitter to base or the base to the collector or whatever. We're just simply bringing earth up and bypassing the transistor. So you could effectively, on LK3 here, and you'd have to probably do it on both amplifiers. Well, actually no, if it's going to the speaker protector module, only one amplifier needs to be shorted to earth on LK3 anyway, to bring the thing into protect. So yeah, you plug a set of headphones in, that will then mute the amplifier, and yeah, you don't have to have an output. You could just simply have, you know, a socket across the output socket on the amplifier and just, you know, do it that way. Oh, but yes, I'm quite impressed with the results of this. The input sensitivity is a little high, but yeah, you get that. So yeah, I'm happy. Now they say if you have an oscilloscope or access to one, you can actually measure what the frequency output of the amplifier is at the VS point with respect to ground, and you should have a square wave output. Now as hard as that is to see, we can see we've got a square wave output, and we got a rough frequency of around 470 odd kilohertz. The operating frequency should be more around 500, and so that's what the output of the amplifier looks like before the filter network, and that's why you would have a 1.5 volt on the output. Now you play the audio, you can see that this is starting to I don't know, dance with the music. And if you pause the music, it remains more stable. And that is how Class D amplifiers work. So if you were to have two of these hooked up as stereo, you would have to get this frequency adjustment almost spot on between the two. So even though I've got the speaker load hooked up across it, I should still be able to adjust this frequency went out 480, 484, 490. Oop, we've just exceeded 500. Albeit the triggering is not all that great. But I gave it about a good 2.5 turns on the pot. Well, I can't get that to trigger any better than that, but we are almost bang on 500 kilohertz quiescent or idle frequency. And it doesn't really affect the output that much. So anyway, that's what I was trying to do before I did the actual output power test, and I couldn't get the scope to work for some unknown reason. I wasn't getting that anyway. But I've changed the USB input for the scope now, and it seems to be okay. The scope's light was flashing red before, it's flashing green now, so yeah, your guess is as good as mine. So anyway, we're around about 500 kilohertz. For all intents and purposes, as long as when you adjust that pot, both outputs have roughly the same frequency on either, then it's not going to be that much of a great issue. Anyway, I'm going to end this video now, just with playing some music. And if you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. And this is the Astro 30 saying, see ya, happy Class D.